we're going to talk about writing equations of graphs of transformed parent functions. And it really fits into the theme of the week, which is, can we identify the transformations so that we can write the equation? And today, what we have is a picture of a graph where we have to identify the transformation instead of the equation where we have to identify the transformation. But what we also need to do is we also need to be able to identify what is the parent function. So when we take a look at this, do you know what the parent function is? And hopefully, you know it's the absolute value of x. Again, I find this one easy to remember because I make a V with my fingers. An absolute value starts with a V. Now that we take a look at that, we've got a couple things, and you do not have to list these in any specific order. We just want to have what's happening to this function. Is there something that you notice right away in terms of transformations? And she says it got smaller, but when it got smaller, it also got kind of taller. It's actually a vertical stretch. Secondly, I think that there is at least one more transformation on this problem. Right 2. I'm going to erase this here in a minute, so I don't know if you want to write this down on your paper. But the parent function of the absolute value function has the point 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. So here's our V-shaped parent function. And again, I'm going to erase that because I'm afraid that's going to get confusing. And actually what I do sometimes is I just put the points in there to look at it. But what we did is we moved that graph right 2, and then we stretched it. And what I want to show you here before I erase this is that when you look at this graph here, what happens is in the parent function, we went one space to the right and one up. But when we look at our new picture, we went one space to the right from the vertex. One space to the right, but we went up 1, 2, 3, 4. And because we went up or down, that's why it's vertical and not horizontal. And our vertical stretch is going to be by a factor of 4. And if you think about it, in our parent function, even though I just erased it, when we went 2 spaces from the vertex, originally we went up 2, but is 2 times 4, 8? And it is. So now we've got what we need in this problem. And once again, vertical stretches are going to be outside of the function. In fact, they're going to be in front of the function. So our equation of our transformed graph is going to be 4 times the absolute value of x, but because we moved right 2, we're going to have to subtract 2. Again, what we're doing is we're identifying the parent function, identifying the transformations to the graph, and then for our final part, we're going to write the equation of the graph. So which graph is this? And hopefully you're thinking y equals x cubed. And when we look at the picture to list our transformations, we just have to list them. They don't have to be in any specific order. We'll get them in order when we put them in the equation, when we write our transformed graph equation in a couple minutes. So the one thing that I look at in terms of this, again, the parent function, I don't know if it's helpful to graph it on your paper or not. I'm going to try this once again. It doesn't jumble up the picture as much as that last one did. But here's our parent function. And even though I'm off just a tad on the graphing, probably because of disorientation, what I look at is kind of the center point. Mostly, it's at the origin. And so where would the origin be on this graph? Well, I think that the origin would be on this point right there. And if we can identify that fact, what we see is we went 1, 2, 3, 4, 5, 6 spaces right. We went right 6. And we also went up 1, 2, 3, 4, 5. Well, there's our first two. As we take a closer look at the picture, what we see from our original graph is that from the origin, we went 1 space to the right and 1 up. So from this new green point that I put in there that's kind of like the origin, we went 1 space to the right still, but we only went a half up. And once again, when we're dealing with up or down, that's going to be a vertical change of some sort. And in this case, this is going to be a vertical compression. And sometimes what we write is, we write it by 2. It's a vertical compression by 2, but what would we put in the equation? And maybe it's easier to say vertical compress in half. But if you see on your practice, it says vertical compressed by 2. What we're going to do when we write our equation, we know that the vertical is going to be one of the first pieces that's going to be in our equation. So our vertical is going to be the 1/2. And then we've got our x cubed. But we're moving the graph right again. And when we move the graph right, we're going to not add, but subtract 6. That's going to move our graph to the right. Don't forget to put the cube. But the right and the left are going to be inside the function. And then finally, we're going to have up 5. That's an outside the function. And that is going to be the plus 5. Now I know our goal is still to not use our calculator, but if you're unsure, type it in your calculator and check the points. Do you have the same points on your calculator screen that you have here? And again, our goal is still to not use the calculator, but if we're checking it, that's one thing, which is different from using it to get the graph. One last function to look at here. And we need to identify the parent function. And hopefully you see that it is y equals 1/x. Once again, I'm going to erase it because it will jumble it up. So I don't know if it's helpful for you to write this down or not. But the parent function for 1/x has the point 1/2, 2, 1, 1, and 2, 1/2. And it also has the point -1/2, -2, -1, 1, and -2, -1/2. So it would look like this. And I'm going to erase that momentarily because I think it jumbles up the picture too much to be able to identify what's happening here. And by the way, there's 2 answers to this problem. But I'm going to do this simpler answer. But what happens here when we look at this, and I haven't talked about it, there's what's called an asymptote in this graph. In fact, there's two asymptotes in this graph, because our graph isn't going to touch the y-axis. And so when a graph is getting closer and closer and closer to something, but it never quite touches, that's an asymptote. And even though it's not going to work so well on my picture, that red graph isn't supposed to touch the x-axis or the y-axis. And the reason that I point this out is because the origin is still important to me when I'm looking at this picture. Because what I want to look at when I'm figuring out the transformations of this picture is, well, where are the asymptotes now? And if this works, and oh, that's not what I want to move here. If this works, I can move this over here for our original graph. I'll get rid of this red graph, and I can move that there. Get rid of the red. I should have gotten rid of it already. But what we can tell by doing that is that I think of it as there's the new origin, so to speak. And all that tells us is, did we move right or left? Did we move up or down? And what this says is we moved left 2. Left 2. One more time. Left 2. And we moved up 1. But after that, we also want to look and see, do we have any stretches? Do we have any shrinks? Do we have any reflections? What I said is that it turns out that there really are two answers to this problem. But the easier way to deal with this problem is when the reflection, because we are going to have a reflection, is outside the function. So the reflection, if it's outside the function, then that means that we're going to have a reflect over the x-axis. And that's all that we have. Again, I know you can't see it on the video, but if you use your hand gesture and take your hand and flip it over the x, it kind of changes it in your mind too, depending on whether you're kinesthetic or not. But once we identify the transformations, then writing the equation, I hope, isn't too much trouble. There's our parent function. The reflect over the x-axis is going to mean that we're going to have a negative in front of the function. The left 2 is going to be associated there with the x. We oftentimes write parentheses with it, but it goes in the denominator, and you don't really need the parentheses there. But it does show the inside of the function. And then lastly, we have our up 1, which is plus 1. So in a moment, and maybe some of you already are, you can turn your papers over and work on a couple of practice problems as I stop the video.